Exponential form or Euler form of complex number is elegant and compact way of representing complex numbers in their polar coordinates. It is derived from an amazing, mystic and most elegant mathematical formula which is known as Euler's formula. Let's start with Euler's formula. Euler's formula states that for any real number x, e raised per iota x equals to cos x plus iota sin x, where e is the base of natural logarithm. It is very commonly used irrational number. Next is the exponential form or the Euler form. Z is equal to r e raised per iota theta, where r and theta are polar coordinates of z. That is, r equals to mod z and theta is equal to argument z. Now from polar coordinates we can write the polar form of the complex number z equals to r times cos theta plus iota sin theta. Using the Euler's formula we get cos theta plus iota sin theta equal to e raised per iota theta. This implies r times cos theta plus iota sin theta is equal to r iota theta. Therefore we get z equals to r e raised per iota theta, which is the Euler form or exponential form of the complex number. Next is de Moivre's theorem or de Moivre's formula. It states that for any integer n, cos x plus iota sin x raised to power n equals to cos nx plus iota sin nx. That is, the power on the left side is multiplied by the angle on the right side. Now using Euler's formula we have cos x plus iota sin x is equal to e raised per iota x. So therefore cos x plus iota sin x whole raised per n equals to e iota x whole power n, which is equal to e raised per iota nx, which is equal to cos nx plus iota sin nx, again by Euler's formula. So cos x plus iota sin x raised per n is equal to cos nx plus iota sin nx. That is our de Moivre's theorem. Let us discuss some applications of these theorems. In the first problem we have to multiply the two complex numbers. Now using the Euler form of this number, we have cos pi by 8 plus iota sin pi by 8 equals to e raised to power iota pi by 8. Now similarly this is equal to e raised to power iota pi by 12. Therefore their product is equal to e raised to power iota pi by 8 times to e raised per iota 5 pi by 12, which is written as next problem is simplify. In this problem we can directly use de Moivre's theorem. The power 20 is multiplied with the angle pi by 15. So this number simplifies to cos of 20 times pi by 15 now cos pi by 8 minus iota sin pi by 8. Its argument is minus pi by 8. So we can write this number as equal to e raised to power minus iota pi by 8. Similarly, the denominator is e raised to power iota 7 pi by 8. So the number is this number, which in turns is equal to e to the power e raised to minus iota pi. Therefore, argument of this expression is minus pi, but it is not the principal argument, as principal argument lies in the interval minus pi to pi, but minus pi is not included. Therefore, to get principal argument, we add 2 pi to this argument, as we can add or subtract 2 pi any number of times to get the other arguments. So in this case, principal argument is pi. Now to solve this, we first of all find the polar coordinates of minus 2 iota. That we have done in the previous videos. I have shared the link in the description box, but I am also sharing a part of it. Minus 2 iota in polar form. So minus 2 iota equals to 2 root 2 times e raised to iota 5 pi by 4, which is the Euler form of this number. Therefore, minus 2 iota whole to the power 8 is equal to 2 root 2 to the power 8. For argument of minus 2 iota to the power 8 is 10 pi, that is also equal to 0. Therefore, we can write minus 2 iota to the power 8 equals to 2 to the power 12 times e raised to iota 0 equals to 2 raised to 12 real. Case. To solve this, we find polar coordinates of root 3 plus 3 iota and iota root 3 minus 1. So for root 3 plus 3 iota, r is 2 root 3 and theta, that is argument, is pi by 3. So its polar coordinates are 2 root 3 comma pi by 3. Therefore, root 3 plus 3 iota can be written 2 root 3 times e raised to iota pi by 3. So for iota root 3 minus 1, its modulus, that is r, is 2 and argument is pi minus pi by 6, that is 5 pi by 6. Therefore, iota root 3 minus 1 can be written as 2 times e raised to iota 5 pi by 6. So the above expression can be written as e raised to power iota times minus 2 pi, but which is equal to 9 by 4 times e raised to power iota times minus 2 pi plus 2 pi, as we can add any multiples of 2 pi in the argument. Therefore we get 9 by 4 e raised to power iota 0, which is equal to 9 by 4.